Hello, in this video we're going to be looking at methods of estimating the area under a curve, also known as estimating this definite integral of a function on an interval. The simplest shape that we can find the area of is a square. So if I'm looking at this curve and I'm trying to figure out how much space there is underneath it, I could just kind of like count up the squares that are underneath that curve. And there's two ways you could do that. I've chosen this method where you can see there's a lot of space that I've missed. So that would be a lower sum, the lower estimate of it. On this one, you can see there's a bunch of rectangles that are sticking out over the edge. So this would be our upper estimate. So we know our actual area underneath this curve is somewhere between 11 and 15 units. The other thing I want you to see about these two estimates is here, if we look at our rectangles, that point is on the curve on the right-hand side of that rectangle. On this one, the left-hand side of the rectangle is what's actually touching the curve. These are called the right-hand rectangular approximation and the left-hand rectangular approximation, but we don't always find them this way. What we are looking for with a lower sum is all our rectangles are below this curve. But if we wanted a right-hand approximation, that means that all of our rectangles should be touching on the right-hand corner of them on the actual curve. So you can see all of these points are connected. In both of these examples, the right-hand approximation ended up being a lower sum. Don't connect those two. These are disjoint ideas. If our curve had been going up, then our right-hand approximation would actually be an upper sum for this thing. But both of our functions have been decreasing, so we have gotten a lower sum from our right-hand approximation. To actually figure out what this is, we just got to like plug in these points and then just find the area of these rectangles. So this first one is 1/2 by what f of 1/2 is. The second one is also 1/2 wide multiplied by whatever f of 1 is, and then etc. down the line. But you can see all these 1/2s. It'd be a lot easier to calculate by factoring out that 1/2. So you'll often see this kind of shorthand trick where, hey, this is how wide all of my rectangles are, and then these are all of the heights of our rectangles. It's just easier to calculate that way instead of multiplying by 1/2 a whole bunch of times. We end up getting a lower sum of 2.66. If we wanted an upper sum for this curve, that ends up being a left-hand approximation, because when we are above, it turns out that the left-hand side of our rectangles are what is touching that curve. Again, left hand and upper are not necessarily connected. If this function had been increasing instead of decreasing, the left-hand approximation would have been a lower sum. We can find the calculations for that left-hand approximation the same way as we did before, where really it's just multiplying all of our widths. So this is width of 1/2 for this rectangle. The width of this rectangle is 1/2, 1/2, 1/2, and then multiply it by these points on our actual curve. In this case, we end up getting an upper sum of 4.395. So we know the actual area underneath this curve is somewhere between 2.66 and 4.395. Instead of doing left-hand or right-hand approximations, we can also try midpoint approximations. Rather than having the left-hand side of our rectangle touch the curve or having that right-hand side of our rectangle touch the curve, you can see how each of these includes a big chunk of area that we don't want. However, midpoint kind of averages the two of them. So then it's just like, okay, we got this part that we missed and this part that we don't want to kind of like average each other out. So hopefully we're not missing as much. So hopefully we can get a more accurate estimate for the area underneath the curve. Usually they'll tell you which one they are looking for when they're asking you to find these approximations. If they don't, then you can choose when you're asked to estimate whether you want to do midpoint, left, or right. But the process for finding this midpoint approximation, you can see, is the same. All of our widths here are 1, so we're multiplying all these widths together. We have to do a little bit more work because we have to figure out, okay, we're not going to go by our width of 1, so 1, 2, 3, and 4. Instead, we want to figure out what's the middle of this interval, so 1/2, and then the middle of this interval, so 1.5. And we're plugging those values in one by one, and we get 53. If we did the left-hand rectangular approximation, we'd end up with an area of 38 because all of our rectangles would be below our curve. If we did a right-hand rectangular approximation, everything would be above our curve. And you can see that these numbers are wildly different from our 53. If we were to find the actual area underneath it, we find its actual area is 53, which is between these two and very, very close to our midpoint approximation. So our midpoint approximation is way cooler and way more accurate than the left or the right. The final method for approximating area underneath a curve is using this thing called the trapezoidal rule. Because what we want is we want a shape that is nice and square on the bottom, because that's easy with the x-axis. And then we want like a slanty thing on the top. Well, hey, that's a trapezoid. Now, the classic idea of a trapezoid is this idiot, where like the two sides are kind of pointing in towards each other. That's not the definition of a trapezoid. Trapezoid just says that two sides are parallel. So the two sides that we can choose to be parallel are our vertical sides. So we're basically taking that trapezoid, turning it on its side, and then making that bottom perpendicular to the other two sides. So we get a nice cornered bottom, but then this nice slant on the top, because that nice slant on the top is going to end up meeting up really nicely with the curve. So we could break this shape up into trapezoids in order to get another estimate for the area underneath this curve. Trapezoids are considered the fastest method to get to a really accurate area underneath a curve. In this example, we're going to apply all four of our methods of estimating the area underneath this curve. So we've got a curve based on this table. I want to figure out the left-hand rectangular approximation, that's the LRAM, the right-hand rectangular approximation, the RRAM, the midpoint rectangular approximation, the MRAM, and the trapezoidal estimate. Let's start with the LRAM. So that means we want our left-hand side of our rectangles to be touching our curve. So we want to make sure we're using this very first point here. That's going to decide the height of our first rectangle. And then our second, and then our third, and then our fourth, and then our fifth, and then our sixth. So you can see we're not going to use that last point because we've already made 6 rectangles. These are the 6 heights that we need. So our LRAM is going to be the width of our rectangles. The width of all these rectangles is 10, because you can see in each one of these we're going by 10. And then it's going to be multiplied by all of the heights. Like each one of those heights is going to get multiplied by 10. So we just got to add them all up. So 1 plus 1.7 plus 1.8 plus 1.4 plus 1.0 plus 1.5. So we got to type that into our calculator. I'll take care of that. So our LRAM is going to be 84. To find our right-hand rectangular approximation, so our RRAM, we are going to skip that first one because we want the right-hand side of our rectangle to be touching our curve. So that 1.7 is going to be our first one, followed by so we're going to get down to the end. So you can actually kind of see, hey, wait a minute, this RRAM is basically going to be that same thing. But instead of starting with 1, we're going to have 1.7, and then and we're going to have a 0 on the end. So it's just going to be 10 less than the previous one. Because the only difference that's changing between our LRAM and our RRAM is this number right here. Everything else stays the same. To find our MRAM, we need the numbers that are going to be in between each one of these things. Our width is still going to be 10, but we don't want our height to be determined by the left or the right. We want what's right in between. So we got to check at those 5-minute intervals that are still 10 apart. So same way, we're going to multiply all of those widths by all of these now as our heights. So now I just got to type all those into my calculator. I typed them in and I got my MRAM to be 90. Now you might notice, hey, why isn't that in between the other two? Is because you can see how our function is kind of like dipping up and down. So it's not consistently going down, it's not consistently going up. So the LRAM and the RRAM are not necessarily the upper and the lower bound for it. So that's our MRAM. All we got to find now is our trapezoidal. So when we're figuring out this area of our trapezoidal, like we could like break it down one by one. And a lot of times we do want to do that, but I'm going to do a little bit of a shortcut. Just like with our LRAM and our RRAM and our MRAM, there was always that width. This piece right here was always that same thing. And we do want that same thing every time. So it's going to be 10. That is definitely going to be stuck out front. Then there's always going to be this 1/2. So that 1/2 is going to be stuck out front. Then I just need to multiply by all of our heights added together. Now, the way these trapezoids are going to work off of each other, say this green one was my first one, the next one would be right next to it. So I use this line right here twice, once for the green one and once for the blue one. So when we get to this 1.7, that 1.7 can get multiplied by 2. And when we get to the next one, this one right here, it's going to be that edge is going to be used by the blue trapezoid as well as the red trapezoid. So the 1.8 gets multiplied by 2. And then we're just going to add these things together. They're not all multiplied by 2, because if we think back to that green one, this green one is only used once. So the 1 is only going to be used once, but everybody else gets doubled. This is just a shortcut trick. You can't use it all the time. But it does kind of make life a little bit easier. So here's how I would calculate out my trapezoidal approximation. Note that I'm multiplying all of these numbers here by 2 because they get overlapped as we move from trapezoid to trapezoid. And then the first number and the last number are not getting multiplied by 2. Not that it would matter with a 0. Now it's just a matter of typing that into my calculator to figure out what this approximation would be. After typing this into my calculator, my trapezoidal approximation ended up being 79. So that one is a little bit more in between the LRAM and the RRAM. That MRAM is probably just because of that switching up and down, that MRAM is not being as accurate as we would have liked. That is it for this video on estimating the area under a curve. Keep in mind these abbreviations. Finney isn't very clear about them. Larson is a lot more clear. That LRAM is our left-hand rectangular approximation, and RRAM is our right-hand rectangular approximation, and MRAM is our midpoint rectangular approximation. I don't think there's a TRAM, but I could be wrong about that. But you should know this area for trapezoid, because trapezoidal approximations get us to the actual area underneath our curve the fastest. However, they are more complicated to calculate. So sometimes just doing an LRAM or an RRAM is just about as accurate as we need to be. Thanks for watching, and I'll see you later. Goodbye.